for the for year 2024. So for introduction, my name is Muhammad Syahrul bin Harun. I'm from Centralized Analytical Laboratory. I'm the person in charge for the cluster of physical. Right. So this is the webinar. The title is Basic Theory and Applications for DSC on polymeric related material research. We are luckily we can have Mr. Josh Lai, our senior application chemist, as our guest speaker, and also Mr. Hazri bin Shahpin, lead technologist for physical cluster. Right. For your information, current aspiration is to promote research excellence by ensuring that the requested analytical services comply with international standards. We are accredited with ISO 17025 2017 under SAM number 544. Besides serving our students, undergraduate and also postgraduate, we also accept and collaborate with industries to conduct testing such as SEM, SRD, SRF, DAC, TGA, and many more. If you have any questions, you may contact us for our services provided, and then our mission to provide an accurate and timely analytical solution with integrity and total focus on our customers' satisfaction. Or if you have any inquiries on our services or testing afterwards, you may contact me or Mr. Hazri, and then we will try to assist you. Right? Okay, this is some information for our guest speaker today, Mr. Josh Lai. He's the senior application chemist. On the applications and some testing, I do contact Mr. Josh, especially on DSC matters. He's also very experienced on handling TGA, DMA, rheometer, TMA, rubber processing products, and etc. He also have a vast experience in handling various analytical techniques such as spectrometers, FTIR, UV, chromatography, GCFID, DCMS, elemental for the SRD, and also SEM. And then we have our staff from CAL, lead technologist, Mr. Muhammad Hazri bin Shahpin. He's graduated from UTM, University of Malaysia, in mechanical engineering in 2020. He has experience more than 10 years in handling testing such as the AC and rheology. So now I would like to invite Mr. Josh for the theoretical webinar today. Mr. Josh, I pass to you.
Thank you, Mr. Syahrul. So I will be sharing my slides.
Thank you.
Okay. So I'm going to minimize this. Very good afternoon, everyone. I'm Josh. So I'm the senior application specialist who based in Malaysia and supporting all TA products for Southeast Asia. So before I start my presentation, I just would like to make sure everyone can hear me and also see my slides. If you can see and hear me clearly, can you please type a yes in the text box so that I know that everything is fine and good to start. All right, thank you for the response. So I'm going to today mainly focus on the theory and application of DSC on a general polymeric related material research. So in this after this presentation, I think Mr. Syahrul will distribute the slides copy to everyone in PDF format so that you can have a copy on it. So today agenda will have altogether 4 parts, which including theory and also instrumentations, calibrations and verifications, which is important because you need to make sure that this instrument is well calibrated before usage, and followed by applications, as well as proper instruments and also sample preparations before conducting measurements with a DSC. So let's begin with part number 1, theory and instrumentations. So these slides will show you all the latest series of DSC, which is our DSC 25 series, and the previous generation T instrument models, which is in blue color, Q series, which is already in UTP itself for Q2000, with or without auto sampler, and this one is the first generation discovered DSC. So this all users of this instrument will be benefit from today basic theory to make you more understanding what you're doing and what kind of result you'll be getting from DSC. So what is DSC to begin with? So a DSC is a differential scanning calorimeter. Okay, so by looking at the name, differential means you need to have a reference sample because you're always comparing the sample transitions and also the reference transitions. So reference, of course, is empty, so it will not have any heat flow change. What is going to have heat flow change will be on your sample, which will directly induce temperature differences. So you're always comparing your sample with a reference. So it's a pairing measurement in DSC. That's why we name it as differential scanning calorimeters. And what does it going to do to your sample? So of course, they are going to either heat up or cool down, meaning that you're doing a temperatures variations. That's why as a function of temperatures. How about a function of time? So a time means you're doing an isothermal test, meaning to say you're holding a temperatures at a single temperature which is constant, and you hold it for a certain period of time. Say for example, you're doing a oxidation induction time, meaning that you want to know the time for a sample to oxidize. So you're going to hold it at a particular period of time for a single temperatures, and then you observe the heat flow change. So whenever you want to do a DSC, you must already understand. So what kind of signals a DSC will give you, which is heat flow differences. So you're going to have a y-axis, your heat flow, and the x-axis will be your function, either time, where you are performing a single temperature measurement, or temperatures, which is you are going to vary the temperatures. Regardless, is heating up, cooling down, or you're doing heat cool, multiple cycle. So a DSC, as I mentioned just now, is a pair measurement. So you always have a pair of inert reference, which is placed on top of this reference sensor, and also the sample sensor. So the sample sensor, of course, you have a crucible or sample pan that will have a sample loaded within the pan itself. While for reference pan means it's empty. So nothing should be, you shouldn't use any sample or reference sample on this reference pan. Okay, so you're gonna have a reference sensor or sample sensor. So what are these sensors doing? Okay, they are actually measuring the temperatures for both reference and your sample continuously when you program the DSC. Ask them to heat up from lower temperatures to higher temperatures at the specific rate, which is a RAM rate. Say, for example, 5 degrees C per minute, 10 degrees C per minute, or 20 degrees C per minute. So you're asking the furnace to induce heat up the sample, or even cool down the sample at a specific cooling or heating rate. So during these transitions, sample will start to undergo transition. So transition can be in terms of physical change. Okay, it can transit from solid to liquid, which is melting, or during cooling from liquid to solid, which is crystallizations or solidifications, or it can induce some what we call chemical reactions, like for thermoset materials. They are definitely going to be cross-linked to each other. So this is what we call chemical reactions or cure reactions. So all these changes in terms of chemically, you're going to have what we call heat exchange. So it's either you are going to release the heat or absorb the heat to undergo certain thermal activity or thermal events. So we are going to measure the amount of energy required for your sample to proceed with their activities. So different sample will proceed different activities, and the DSC are able to give you the amount of heat or energy required for them to do that. Okay, and besides that, DSC will also tell you at what temperatures your sample will perform the thermal activities, which in other words, for example, for thermoset, you are able to know the curing enthalpy, the amount of energy is being released when you form the bond in the curing process. And you can know also the curing temperatures, at what temperatures the reaction started. Okay, similar to physical change like melting, crystallization. So you can know that the crystallization temperatures and the amount of energies that been released during crystallization process, as well as melting process, which is the other way around, from solid to liquid. Okay, in a DSC, we have a very special name for them. We always have a bombastic name for specific equipment. So endothermic response means heat entering the sample. So that's why we name it as endothermic response, meaning heat being absorbed. Transitions examples will involve melting. Okay, so because melting, you need to break the bond, so they're going to acquire the heat, they're going to absorb the heat. So melting is one of the endothermic response. So for exothermic means the heat will be exit from a sample, such as curing, which involve bond formations, not bond breaking. Okay, bond breaking absorb heat, bond formation to release the heat. We also can use DSC to quantify the amount of energy being released due to bond formations like curing. Okay. So when you're going for DSC, you must ensure that you must be ensuring that the transitions that you want to measure in heat flow changes. Okay. So how does a DSC result look like, or endothermic result look like? So as I mentioned, the y-axis is what you are measuring. So we are measuring heat flow changes, while the x-axis is a function, is your predetermined method setup. So it is going to be time function, signal temperatures, or temperature function, which is you're going to heat up the samples. So we are going to have a recorder to record the temperatures. So from here, you can see the changes. And very important notes for everyone in DSC analysis, you must look at this a note. So all DSC results, regardless from TA or others brand, you definitely will need to have this nota kaki. So like keynote that you can see exo up. So if exo up, all peaks then going up, we consider as exothermic transition. While the other way around, facing downwards, will be your endothermic. Okay, so endothermic means you are going to have a sample to absorb the heat to undergo their thermal activities. So it will be involve heat capacity, TG, softening point, melting, and evaporation, as well as other processes as well, which including a TG, which is the most common measurement parameters that use DSC to do so. Well, for exothermic, as I mentioned just now, involve bond formations, so including the heat capacity changes upon cooling, crystallizations, curing, and in most cases, oxidation as well. Okay, so it will be like exothermic, so it's facing upwards. So some result that you read from journal may be exo down, so you need to be very careful on this, even in T instruments result, people can change the directions of the meanings for exo and endothermic response from a DSC. So a DSC heat flow. So DSC heat flow is actually a result. Okay, so this is what you're measuring. So this is what you are seeing in your y-axis right here. dH dt, usually in milliwatts, watts per gram, or any other units, but they have a similar meanings. So watts means what? Joules per second. Okay, and this heat flow in general will depending on two factors. Okay, first of all is your CP, the sample heat capacity, because you're asking your instrument to heat up the sample for every minute. So the amount of heat required to raise your sample temperatures will be related to your CP. So CP is a material constant. So different materials will have different CPs. So you're going to get some difference in terms of heat flow in order for you to achieve your settings, okay, your methods. And of course, besides the sample heat capacity, it also depending on your heating rate. So that's why you're required to use a single heating rate only, or analytical heating rate only, when you are trying to compare your samples. Okay, you cannot compare a sample run with 5 degrees C per minute and then another one with 20 degrees C per minute. The curve will be different, okay, because it also depends on heating rates, plus some kinetic events that happening in your sample, which is more like occurring reactions, okay, which will be involving the time they spend at that particular temperatures. So total heat flow change will be depending on these two factors in general, okay, depending on what thermal activity that your samples is undergoing at that particular temperature range that you are measuring, okay. And of course, in DSC heat flow, for physical transitions or chemical transitions that involve heat capacity changes would be your TG, most probably TG, and also your melting. Okay, well, for kinetic event, typically will involve crystallizations, a little bit of melting, cure reactions, volatilizations, decompositions, and also denaturations. Okay. Well, a dedicated DSC, meaning to say, if you are having a DSC that only can do DSC work, you are not allowed to decompose your sample within the furnace, given the possibility for your polymers or your components release acid film. So these acid films will eventually corrode the furnace, because the furnace is made from silver. Why we use silver? Because silver is the top thermal conductivity materials, okay, metals. That's why we use silver as our furnace to efficiently heat up the samples without any thermal lag, okay. Well, I mentioned just now, DSC, we can do isothermal, we can do temperature variation, but the temperature variation is not limited with heating only. We can also do cooling. That's why we need to have a cooler attached to a DSC. Okay, even you don't do cooling, but you still need to turn on the cooling system option, given that you need to have a heating element that work together in a synchronized way with the cooling system, so that you are able to control a heating rate at your desired RAM rate, say 5 degrees C per minute. So I need to increase my sample temperatures just nice, 5 degrees C for every minute, okay. Of course, we have multiple chiller options or refrigerated cooling system options to cater for different temperature range requirement for your measurements. And the ACS or RCS right here, you do not need to have any LN2, okay, when work with subambient. But we do have options that if let's say negative 120 is still not enough for you for elastomeric materials especially, then you may go for LN2 accessories. And for some users that do not need any sub-ambient operations, but you want to have a slightly above 400 degrees C, you can use a fin air cooling system. So the DSC itself can actually compatible with a different kind of cooling options. So let's move on to part number 2, which is calibration and verification. So in order to make sure that your instrument giving a reliable result, of course, you need to do calibration and verification. So how do you do it? So what type of calibration and verification that we need to do will be depending on what kind of thickness that your samples is recording. Okay, so a DSC, as I mentioned, they are going to measure heat flow. So we need to calibrate and verify the enthalpy, which is the energy being quantified is correct. Secondly, we're going to record the temperatures. So that's what we also need to do, temperature calibration and verification. So you need to calibrate and verify with internal standard, okay, for this case. Well, we have different models with different features. That's why some models that you require to do T0, some calibration you require to do the baseline. But all DSC, the most important one will be on your cell constant, which will calibrate for your enthalpy. So you are going to make sure that your DSC is giving you a correct enthalpy, okay, amount, and also the temperatures that record where the thermal event happened. So the most common standards materials that being used is indium because it is abundantly available on Earth. You can get it easily and it can be reused. Of course, if let's say you go through other ASTM method, some may also include other metal standard as well, like zinc, like stannum, like maybe other metals. But this kind of metals, first of all, it's not abundantly available and it may be more expensive and less stable, that you have a shorter storage period and it cannot be reused. So you need to be very careful when using others metals as a calibration constant, okay? But in TA instruments, we are allowing you to have more than single point calibration up to 5, okay? So calibration is required depending on the usage, but generally every month if you're hardworking, but at least you need to do it every 3 months, okay, to verify the system is giving you a reliable results. Just imagine a DSC is a furnace, it's a heat cool for many times, so the furnace will not be the same as you bought it when you're first time using it. It's not going to be the same, so that's why you need to calibrate it periodically, okay? So prior the calibrations or any calibration, you need to first of all to dry the cell. So let's say you close it for over the weekends, you need to hold the cell at 75 degrees C for 1 or 2 hours to remove all the overnight moistures, residue, or even solvent that evaporated from your samples. Okay, so for T0 calibrations is for those DSC that have a flat baseline features that you do not need to do any blank subtractions. So you need to perform empty cell, dual sapphire disc, as well as temperatures and cell constant calibrations. So this indium is most common. Okay, usually it will come with a certificate, but there are some that come without a certificate. Then you can use this value as your reference. Okay. And DSC is not only the instrument that you can, it's not only measuring the heat flow, you can also measure heat capacity as well. But this one, you need to use a sapphire disc as your calibrations materials.
Mr. Josh, may I interrupt you one second?
Okay.
Okay, actually for my DSC, right, we have every annually we conduct calibration and maintenance per year. In,
Okay.
ter- in terms of accuracy, is that already enough? Once a year or twice a year, we conduct PM.
Okay, PM is different for you from user calibration, yeah. PM is for engineer to check the hardware, and of course it will do a calibration and also verification for you. That is PM, okay.
Okay.
But for user, it's your responsibility to verify the system every month or every 3 months minimum
Mm,
with this
okay.
one, okay, to
If
check,
we if we
to
avoid
check.
this to check, right? Alright, please continue. Okay, please.
Okay, you need to check with the verification first. If the verified result is out, then you go for calibration and re-verify again until you get the correct one. So you need to do every 3 months lah, minimum, to make sure that your equipment is still in a good shape. So you need to verify every a month. So this indium here, besides verify for temperatures, so you're going to compare with this the temperatures, you also will eventually need to calibrate for the cell constant. So cell constant typically is a correction factors that use to correct your enthalpy readings. Okay, when you do the integration for crystallization, for melting, you always have a delta H, right? So that delta H is being corrected by this constant. So this constant is also obtained by doing the calibrations by using the indium. Okay, that's why in all ASTM, when you read, calibrate with indium standard for temperatures and cell constant for enthalpy. So typically in a N2 purge, which is a purified nitrogen gas purge, it should be lies within 0.9 to 1.2. If over this value or below this value, then you need to consider to clean the cell with a fiberglass brush and redo it again. Okay. So this is a calibration result example. So this is how the result should look like for indium. All right, from here, and then you're going to have a calibration result like this. Of course, this is a literature review. Sorry, this is a certificate reference value. So the TM for indium melting temperatures is 156.6 degrees C, and the enthalpy should be 28.71. So now you're doing calibration, meaning that there's no correction factors applied to it yet, because in calibration step, you are trying to find correction factors. Okay. So this is the calibration result that you get 158.27 your PM. Okay, right here in the indium we take the onset, not taking the peak. Okay. So you'll fill in this into this what we call temperature correction factors, and it will adjust for you with the software. So beside the temperatures, you also need to input the enthalpy. So the enthalpy that we get is 27.52, but the correct value is 28.71 joules per gram. So how the cell constant being calculated? So it's actually using 28.71 over 27.52, and then you get this 1.043. The software will do it for you automatically. In this presentation, I'm just showing you how the software doing it, where I get this 1.0, where I get this 0.9, okay? So that you are aware on it. Of course, you do not need to use a calculator to press anymore. It will just show you after the calibrations. Okay, after the calibrations, not enough. Okay, after you apply this cell constant, after you apply the temperature table, you need to re-verify, just like you're doing a sample. Okay, you treat the indium as your sample, repeat the run again. Okay, so now you see it become what? After the correction factors applied, it become 156.59. which is plus minus 0.01 degrees C, okay? And then 28.66 joules per gram, which is very close to its plus minus 2% variation. Then this DSC is being calibrated and verified. So the result that you get from a sample will be correct. So this is how we actually make sure the DSC is in a good shape. And this step should be done by the user. You're not going to wait for engineer come in every year. If you do it every year, throughout the year, the results, you do not have any proof that whether the instrument is still in good shape or not. Just like you do a body checkup, okay, for human, 6 months, but for instruments, every month if can, minimum every 3 months, because the furnace is being heat up, cool down many times. So you need to make sure that they are still giving you a reliable result. So this is very important. Okay. So that's what I mean by calibration and verification. Calibration, you're attempting to find out the correction factor. Verification means you want to prove the correction factors is working for your instruments to get an accurate results. All right. So I hope everyone in this room for very clear with what is calibration, what is verification, and these terms apply to all others instrumentations equipment as well. You need to first calibrate, find out the correction factors, and then verify the correction factors is working for your instruments to give you an accurate results. Okay, so as usual, you run an indium, and indium you have a known value. If it comes with certificate, then you need to refer to the reference material certificate that you get this value within certain acceptance range. Okay, of course you're not going to get exactly 156.56. Maybe it will 156.58. As long as within the variance, then it's considered in a good working conditions. Okay. Okay, beside verifying the temperatures and also the enthalpy for the cell constant, you also need to make sure the cell is clean. Okay, how do we make sure the cell is clean? Remove everything, remove samples, pan, remove your reference pan, let it empty. Just heat up 20 degrees per minute from room temp, from lower temperatures all the way up to 400 degrees C. We should be getting relatively flat baseline. I do not want to see any spike in between. Sometimes you have a peak, exotherm, endotherm. Nothing should be happen because the cell is empty. It shouldn't have anything. If it shows something, means your cell is contaminated. So you need to break the cell. You need to try to clean the cell. Okay? Otherwise, somebody decompose something inside the cell. You are having a huge transition right here. Then this portion may fuel all your weak transitions. So this will reduce the sensitivity of your instrument. Okay. So now we need to verify the baseline. Of course, this all can be done by software at the latest series, Discover series, automatically. But what we do is actually we want to measure the drift. So the drift is actually a deviation from the straight line. Okay. A perfect baseline is a straight line in 0. Okay, perfect. But this is an instrument. Okay, it's not going to be perfect. It still have some noise, but must be within must be very minimum. Okay, we want to keep it to a minimum so that all small signals can be detected. So it should be eventually less than 50 microwatt. Okay, micro, not milliwatt. Yeah, micro in the bow area, and the drift, meaning the drift means from the minimum to the maximum should be less than 50 microwatt. So for this case this is milliwatt, so it times 1045 and 32, so it's okay. So for baseline check, you can Baseline check is also important. You can do it every 3 months, and you can always check you can compare the latest baseline with the previous baseline after the calibrations to check whether they are still good. In Q series, you may need to do this manually, but in the latest Discovery Series 25 series, all can be done automatically for both calibration and also verification. Okay, they will tell you whether this indium test is pass or fail. They will tell you also the baseline is in good shape, or you should recalibrate it again. Okay. So this is the criteria to actually to verify the baseline. So you just run the empty cell, full temperature range depending on your chiller, and then you can plot milliwatt versus temperatures on a plus minus 1 milliwatt scale. Okay, you can plot it. In Q series, you may need to plot it manually. Again, in the Discovery 25 XX series, which is our latest series, all will be auto. Okay, so this should be less than 50 and less than 50, and should look fairly flat and should be aligned around 0, not any other places. Okay, so you need to verify performance periodically. So after verifying, this is what we found. I'm doing this manually because I'm presenting. So in the software, they will do it for you. Okay, so that's all for the calibration and also verification parts. So now I'm going to move to application. So now your instrument is ready for running sample. So what are these? What are the most common DSC applications? So application agenda will include for polymeric materials like thermoplastic. You always have a TG, what we call the glass transitions temperatures. Okay, TG. For thermoset materials, of course, it will be involved curing and cross-linking. And also for thermoset, food samples, wax samples. So you may have or oil samples. Okay, you may interested on the melting and also crystallization analysis. Okay, so I'm going to cover this in this application sessions. So again, just to recap what you have just learned in the theory part. So a typical DSC transition, you're going to have heat flow on your y-axis. The x-axis typically will depending on what test you're going to do. The most common would be heating, cooling. You're going to have a temperatures variations on your x-axis. While for isothermal, you're going to have a time scale. Okay, and also exo up. So in TA by default is exothermic up. Okay. So for TG, typically initially no transition, nothing happened. So temperature when it heat up, it will be relatively flat. It should be relatively flat. Okay. Of course, in real situation, you will have a startup hook. Okay. And then you're going to have a step-like transition, softening point going down. So going down means endothermic, which is your TG, absorb heat. And then after the TG, you go forward further, and you have what we call crystallizations, okay, going up. So it's exothermic. After crystallization become crystal, you further heat up the crystal, you're going to melt, going down. So going down means endothermic because exo up. Okay, so this is thermoplastic. For thermoset, how? Thermoset is like this. When heat up is curing, it forms bond in between them to form three-dimensional network. You have a lot of new bond. So you have a very broad and huge exothermic peak because when you form bond, it will release the heat. Okay, and then when you further heat up thermoset materials, they're going to decompose or oxidize. So depending on the pitch test. So this is how we eventually read DSC typical transitions. Okay. So let's begin with TG. So TG is actually defined as a glass transition is a step change in a molecular mobility. only appear when you have significant amount of amorphous phase in your sample, okay, which will result in a CP change. During these changes, the material is going to turn from rigid when they are below TG to soft and rubbery states. So the amorphous materials, they will flow too, but they do not melt. So there's no DSC melting peak in TG. TG will look like a step, just like this one, okay? So the change in the heat capacity at the glass conditioner is a measure of the amount of amorphous phase in the sample. So you can also measure the amorphosity with this CP. And sometimes you have what we call enthalpic recovery, okay, in your glass transition. So you see a huge peak right after the TG itself. So this is a polystyrene materials. And again, you can use DSC to measure the heat capacity right here. So you can have a mirror images of both. So temperature below CP means what? What you expect your chemical or physical properties of your materials at a temperature below CP, below TG. It will have lower CP, it will have lower volume, lower CTE, higher stiffness, because hard and rigid, thicker consistency, more brittle, and lower enthalpy. Okay, if above TG, it will be in the opposite directions, opposite of these descriptions. Okay, so when reporting a TG, very important, and as also mentioned in the ASTM, so the molecular motion should associated with TG is time dependent. Okay, therefore TG increases when heating rate increases or the test frequency. Test frequency is more related to the DMA, which I'm not going to cover today. That's why it's important for you to use a consistent heating rate, because TG will be shifted when you use a different heating rate to the right or to the left, depending on the increasing the heating rate or reducing the heating rate. And also when reporting a TG, it is very important for you to state what method, what instrument you use, and what experimental condition you use, and how the TG is being determined. So these are the three factors that you need to report in the TG, because all the TG result, TG is actually a range of temperatures, but usually people just like to present them in a single point. Okay, so that's very important. So TG can be analyzed as half height, okay, as you can see from here, extrapolated onset, end-set, or half height, inflections, okay. So we have multiple choices on how you do it. That's why you need to, when you present the data, you must report all this, how you capture the data. Okay, so how do we measure amorphosity from step change of CP? Okay, so let's say this is a PET. I have a quench cool PET. So this is a quench cool PET, means I assume I'm going to have a cooling rate very fast, 285 degrees C per minute. We quench it. We make them, so we'll put a quench PET into the DSC, and then we calculate the CP change. Very big, okay, which is around 0.3527, so around 0.353 right here. And I want to find out a control cool PET will have how much of amorphosity from here. Again, I can check the CP change right here, and then ratio up with the 100% right here. So 0.145, okay, over the 0.353. So I get 41%. So if my PET being cool, control cool at very slow cooling rate 0.2, I still have around 59% of crystal appearing to it. Okay, so this is how we calculate the amorphicity by using the CP change. And a very important note for you to take note is a glass transition is a reversible transition. So when you heat up, it should show a step. When you cool down, you should show another step. If you heat up again, it will show another step. So it's a reversible transition. And this is the way that you want to verify whether this is a TG or other transitions. Okay.
Mr. Josh.
Yeah.
So this one we call it a 3 cycle, right?
This one is only 2 cycle, but you can do 3 cycle, heat, cool, heat.
It could hit lah.
Yeah.
For those handling the DSC, right? They will they are familiar with 1 cycle, 2 cycle, or 3 cycle test parameter. For this one, we set this one for the two cycle, right?
Yes, for
Hmm.
your 2 cycle.
It looks because I looks it like 3 cycle actually, but that's okay. Alright, please proceed. Thank you, thank you.
Okay, so now I'm going to show you the effect of heating rate on TG. Same sample size, but different heating rate. So you can see the step change of the step change from a TG getting more and more obvious at high heating rate. That's why in ASTM, they recommend you to use 20 degrees per minute instead of 2.5 degrees per minute to capture TG, because it's way more sensitive when you use a high heating rate. Remember, the heat flow change is equals to Cp times heating rate. In other words, Cp is a constant. So heat flow change will be directly proportional to the heating rate, whereby increasing heating rate means increasing the DSC sensitivity. Okay, this is important from the equations. So if our heating rate, again, you're going to have a higher heating rate, so you can get a more obvious TG, but at the same time, the TG will be shifted to higher temperatures. That's why when you want to compare sample TG, you must use identical heating rate. But TG is not the only, DSC is not the only method that measure TG. You can use DMA as well, especially for highly filled materials, or you can use an MDSC. But DSC, standard DSC is the most common method because it's easy to prepare sample, because just crush it, just stuff it inside the pans and then just run it. But for DMA, you need to prepare a specific thickness and specific weight and shape of your samples. So what will affect the TG? Heating rate, which I've just mentioned, heating and cooling for many times, aging, molecular weight, plastic sizer, filler, crystalline content, copolymers, site change, polymer backbone, and hydrogen bonding. Anything that you could think of that will affect the molecular mobility will eventually affect the heat CP, and also if you affect the CP, then it will definitely affect the TG. Okay, anything that affects the mobility, because TG is about transitions of mobility. Okay. So again, TG is due to the amorphicity of the materials only. Crystalline materials will not have very obvious TG. Okay, it will have a very small TG only because it does not move at all, because crystalline materials are very packed together. And TG should be reversible, and it should be a step change in CP, which can be detected by a DSC as well. Okay, now I'm going to move on to the curing and cross-linking. Okay, so unlike thermoplastic, you also will have a curing. So this is the first heating. We'll have a curing here, and then you have a second heating. So after the cure, less mobile, so the TG will be increasing. So typically, this is an example of the curing for epoxy for 48 hours. So you can see after curing at outside externally for 48 hours, you have the curing here, and then you cool it down, and then you heat up again. So the curing peak disappeared. Okay, it's already So thermoset is something like you harden, you cure it, and it's not reversible. So unlike thermoplastic materials. Okay, so you can calculate percentage of cured by using DSC. So typically you can run an uncured materials in the DSC and run a partially cured sample that you want to test that how much curing is being made from my samples. So you can use this formula. If you let's say you want to measure percentage of cured, you can use 1 minus residue cured over full cure. Percentage of uncured, you can use delta H of residue cure over full cure. So you must get a full cure here. For example, an epoxy that being cured for 17 hours externally. I want to check the curing percentage of my sample that are being cured externally. So first of all, I need to check the 100% curing behavior, enthalpy, and then my sample with the residual cure, meaning that it's still not fully cured. So I want to check 17 hours, how much cure that are being achieved, has been achieved by the oven. So you can fit into this formula. So it's around 79.86% only. Similarly, you can use this method to check the percentage of cure of your thermoset as well. While for melting and crystallization, so this will back to the thermoplastic materials. So for thermoplastic materials, usually it's semi-crystalline. Okay, so in the crystalline phase, it's orderly arranged. Okay, usually it's melting, TM, right here. And for amorphous phase, usually it's randomly ordered. Okay, so this one will actually appear a peak in your DSC signal, but this one it will be like a step, like I just mentioned in the TG sections. Usually, TG will happen at the lower temperatures than the melting temperatures. Okay, so semi-crystalline means you have some parts is crystal, some part is amorphous. So you can check. So previously I've told you that how you want to measure the percentage of amorphosity. So in this slide, I'm going to show you also how to measure initial crystallinity of a thermoplastic materials that you produce. Okay, so study of melting and crystallization using a DSC. So you need to understand what are the terms of all this. Melting is a process of converting solid, which is a crystalline structures, to liquid amorphous structures. Okay. Well, crystallization is a process of converting solid amorphous structures, okay, or liquid amorphous structures into a more organized crystalline structure. So this is a true definition, okay. And melting usually from solid to liquid, and crystallization the other way around from liquid to solid, okay. So we will integrate these peaks on a time basis to determine what we call the heat of fusions, or what we call the heat of crystallizations. So this is how it look like in the appearance. So you should have a melting. Okay. When you do cooling, you should have a crystallizations that happen around the same temperatures. Not all endothermic peak is melting. It can be evaporation, okay? If it is evaporation, you heat up. When you cool down, what will happen after evaporate? This will reflect. There's no crystallization occur, so there's not a melting. So this is how we actually generally verify whether this is a melting or not. Like indium, also you have a melting peak. Okay, if let's say you cool it down, of course you're going to have a crystallization peak for the indium as well. So why indium we take onset, while polymer we need to take peak. So in ASTM already mentioned, for any low molecular weight materials, which is less than 500 grams per mole, we need to use onset. Okay, above that polymer, which is 100,000, 200,000, then we use the peak. Like this, melting of PET, we need to use the peak, and this is the heat of fusions. Okay, and you can see from here, a pure material usually will have a very slim peak. okay, because all are the same. But for polymer, they are different. Polymer can be synthesized in you have branch polymers, you have polymer with different polymer chain length, and depending on how you synthesize them, and also depending on how you cool them. Okay, even for PET, quench cool PET will give you different result from a control cool PET. And for crystallinity analysis, it's very common that you need to understand some common terms like amorphous phase. Okay, so it's a portion of materials whose molecules are randomly oriented in space. They are randomly oriented, Versalera. Okay, they can appear like a liquid, glass, and also glassy or rubbery solid. So typically, this will appear on the thermostats and also some thermoplastic. Okay. For crystalline phase, the portion of materials whose molecules are regularly arranged into well-defined structures consisting of repeating units. Okay, they are very ordered. Okay, they are very packed. But in real, very few polymers are 100% crystalline. Okay, usually they are semi-crystalline, depending on the percentage. Okay, which is most common in the thermoplastic world. So some analog terminology which is also important, which is the thermodynamic melting temperatures. So thermodynamic temperatures is what we're measuring in TM, which is the temperatures when a crystal would melt if it had a perfect crystal structures, meaning that during the cooling process, during you produce the solid, okay, is in a very perfect shape in their best conditions, okay, best crystal. So, and then this crystal melting at their original melting temperatures, we name this as thermodynamic melting temperatures. But in some cases, maybe the process is not ideal. You may produce metal stable crystal, meaning that same materials, but the crystal that you produce is not in their own perfect shape. You have crystal, yes, but with defects. So this crystal is not perfect. Then it's poor in quality. So they will melt earlier, which is lower temperatures in relative to their original thermodynamic melting temperatures. So it's pure quality. So we name this as metal stable crystal. And we also will see some other phenomenon, which is what we call crystal perfections. So what's crystal perfections? It's whereby a process of this metal stable crystal melting at the temperatures below their original thermodynamic melting temperatures, and then recrystallize again into a more perfect shape and remelt again in higher temperatures. This will occur in the DSC, okay, without you noticing it, okay. So crystal structures is typically analysis is being broken down during the process of melting. So the process of crystalline structures, okay, or crystallization can occur during heating or cooling. So you have two. Cold crystallizations. Usually you will see this phenomenon for those materials that being quench cooled. Okay, use a quench cooled thermoplastic, put them inside a DSC, you see this phenomenon. You will see when heating after TG, suddenly you have a exothermic peak. That peak will not reappear because it's just a rearrangement of the amorphous material becomes more ordered. Due to the quench cool activity, meaning that they are being cooled rapidly, they do not have enough time to arrange themselves back to crystal shape. So they froze there, froze in space and become amorphous. So when you put them in the DSC, you heat them up. After the TG, the materials become more amorphous and they become mobile because of mobility. So they are going to rearrange themselves. So the rearrangement right here, we name this as cold crystallizations. Okay, that's why it occurs on heating. For crystallization, it will occur on cooling. So after the material melt, you cool it down, so they're going to undergo solidification, or what I call crystallization. So we have different names for different process. Okay, so typically the amount of energy required to melt structures is equals to energy being released when you create a structures. So these laws must be obeyed. So like here, a typical heat-cool heat thermogram. So you'll place a quench PET right here. So you have a first heating, you have a TG, and then you suddenly have this cold crystallization peak. And then you have a melt, okay? And then you cool it down again, and then you heat again. So the TG disappeared. Why? Because all turned into crystal already. Only amorphous will contribute the TG. So the TG will lost. No more rearrangement, and you can see the melting shape also different. So you have some metal stable crystal right here. You can see it melt before the original thermodynamic melting peak. So how do we calculate the percentage of crystallinity? So sample must be pure materials, okay, not a cold polymer or filled polymer here. So it's already mentioned how we calculate crystallinity in the for thermoplastic materials in ESCM. So you must know what? You must know the delta H, the enthalpy heat of fusion of your from the literature, okay? And for sample that come with a cold crystallization, you can use this formula. How do we get this? A very good question. So if let's say today you synthesize polyethylene, okay, so you need to calculate polyethylene delta H from the literature. But today I'm going to use a PET as an example. So you need to go to this what we call ATHAS data bank to calculate, to source out the delta H fusions from common polymers from this data bank. How do we do it? For example, for PET, you have these structures recognized, and then you need to calculate what? The molecular weight, the relative molecular weight. 1612 H is 1, and then 16, you sum up, you get 192 grams per mole. And then you have this data sheet, which is delta HF, heat of fusion in kilojoule mole. And then you ratio up 26.9 times 1000 so that it can be in joules over 192 grams per mole, which is you calculate from here, and you get 140 joules per gram. So this is your delta H literature, okay, for PET. Now I have a quench cool PET. I want to calculate my crystal percentage for this sample that I received. So I put in the DSC, of course. And then very quickly, I get a TG, of course. You get a rearrangement here with a cold crystallization peak, and then followed by melting. And then I use back this equation. 100 times what? Delta M, 74.71, minus cold crystallization delta H, 53.39 over 140 that I get. So I only get 15% of crystal for my sample that I received. So this is how we calculate it. So this is a PET after cooling and at a different rate. As you can see, different cooling rate will form different crystal perfections. Okay.
Sorry,
so
Mr. Josh, can you repeat this the previous slides, please?
You mean this one?
Yeah.
Okay. Okay, so we have a quench PET. So now my objective, I want to calculate my quench cool PET crystal percentage. Okay, I received this sample from my customer. The customer want to know this PET percentage, crystal percentage. So very immediately, I cut the PET, put them in the pan, and quickly ramp up. So I get this result. Because the quench cool PET, so I will expect you have a TG, and then you have a whole crystallization peak. Okay, And then you further heat up, you have a melt. So how I calculate it? First of all, you need to get the delta H literature by using this method. You need to go for ETHAF data bank. Since it's a PET material, it's pure materials, okay? Very quickly, I need to access to this PET. Maybe you need to pay for this data bank here, and then get this data sheet for PET. So this is a crystalline calculated data, okay? Everybody is using this. And this is a recognized structure for your PET. So you need to sum up based on the structures for this relative molecular weight. So it's 192, 16 plus 12 plus 16 plus 6 plus 4 plus 12. So plus everything together, you get 192. This is your delta H literature, okay, 100%. So in order to calculate this, you have this data sheet 26.9 in kilojoule per mole. In order to convert them into joules per gram, you use the 26.9 kilojoule per mole times 1000 over 192 grams per mole that you calculated just now. You get 140 joules per gram, meaning that 140 joules per gram is your 100% crystal heat of fusion for PET. All right, you capture that. Now, going back to this, I get this quenched PET, I put them inside DSC, I heat them up, I get this result. A TG, a cold crystallizations, and then a melt. Now, my intention is to get the crystal percent of my quenched cool PET with this result. How am I going to do it? Use this formula, 100 times 74.71, which is your delta heat of fusion. From here, you do the integration, minus 53.39, the cold crystallization delta H over 140, which is what you calculated the delta H literature. So my quenched PET only contains 15% crystal. All right.
Yeah,
You
well
could,
understood. Yeah, well
yeah.
understood. One more thing, one more question that I'd like to ask you is that when you calculated the 15 percentage of the crystallizations of PET, what
Yeah.
about, let's say, we have got a mix of other substance in PET? Let's say, for example, we have mixed with any ceramic into that. So in that sense, how to compute the crystallizations of a composite materials then? Thank you.
Then you're not allowed to do that because it's already mentioned here. Pure material, not copolymer or film, and no other materials should be inside. You can only calculate by using pure materials. So this is basically for those people that want to synthesize polymers with different catalysts. Yeah.
Thank you. Cheers.
And this is a method that being recognized in ESDM as well. I just summarized it. So make it quick. Okay. Okay, for the last part, we still have I will just overtime a little bit. So the last part will be a sample and also instrumentation preparations. I think this is more to a lab technician part. So typically, you need to prepare the instrument with a push gas. You need to use N2, purified nitrogen gas. Okay, in the case that you want to use any oxidative gas, you can use air or O2 or even helium. Okay. Cooling accessories, if the asset is being shut down for overnight, then you need to do self-cooler conditioning. Otherwise, you don't need to do it, and you need to warm up at least 15 minutes. Should be fine. Sample size. So you need to be very careful on sample size. You can see from here, if let's say you want to do a TG measurement, DSC has a least sensitive. So we need to combat that. You need to increase sample size. So you can see from here, the TG for most materials is obviously on the high side, above 10 mg. Okay, for melt and cure, typically 5 mg should be enough. For pure materials like organic materials, like pharmaceutical materials, very pure, 100% pure, you really do need to put a lot of sample. So 0.5 to 5 mg would be enough, because this kind of sample is very expensive as well. Okay, and also a very reactive sample, typically it can weigh less than 0.5 mg. TGO press, typically you have a low mass pen, and then you have a standard pen. Okay, right here, typically this kind of pen, typically you can use for both liquid and solid materials, but it will depending on whether you want to hermetically seal it or cream it. So for TGO lid, typically it's for dry sample, solid sample, powder sample. For hermetic lid, typically for wet sample or paste sample or semi-solid. Sample shape must be kept as thin as possible, and you must make sure that the sample is touching the pen bottom, not at the side. Okay, so this is where the heating will be going on, so it will directly heat up the samples. So if powder spread evenly, if a pellet, then you can cut and slice too and make sure it's flat. Okay. Avoid using a very thick sample. Please do not put a bulky sample directly on it without crushing it, because this will happen. You always have a cool zone. If let's say you have a cold zone, then all your transition will be shifted to higher temperatures. That's why in DSC, you must be consistent in your heating rate as well as sample size. Please do not overlook sample size, okay? So sample preparation, since you must follow the recommended weight, the more weight you put in, the CP, the heat will work very hard. So let's say you have one sample, you load 1 mg, another sample you load 50 mg. Both of these samples, 50 mg will have a very huge and large startup hook, okay? Then you may not have a very nice result, yeah? So for precaution, you must think before you load the sample. Run the TGA first, okay? To avoid any unwanted decomposition happen in the DSC, okay? Know your expected transition temperatures. Must start 30 to 40 degrees C before the transition happen and after the transition happen, okay? Do not just heat and cool at that particular TG point. This will not give you a result at all, okay? So must keep the DSC clean. Do not decompose any sample in the DSC, okay? Unless you're having a DSC TG instrument, means simultaneous 2-in-1 instrument, you can do that. With a dedicated DSC, you cannot do that, okay? So let's say it's 380s in the TGA, okay? Then you should stop at 350, at least 30 degrees C gap, okay, from your first weight loss that you detect in the TGA. Clean the cell, you can use solvent, okay? If you do not have solvent, you can use this provided brush to brush the stain or any residue from a sample. And then kindly use a handheld vacuum to vacuum off. Don't use your mouth or blower to blow off this fiberglass. This is a glass, it's carcinogenic, yeah? If still cannot remove, then the last procedure is to heat up the samples, heat up the empty cell up to 400 degrees C for discovery, 550 degrees C for Q series, with the air purge or with the oxygen to try oxidize the residue out from your furnace. You can always check out our TA tactic. We have a lot of videos to show you how to operate a system. We have our own webinars in our websites to allow you to access 24/7 without any charges. It's FOC. Okay. Thank you very much. That's all for my presentation. For if you have any questions, feel free to put in the emails or something. Yeah. So I believe we have another sessions right coming on. Yeah.
All right,
from
thank you very much.
Hannah.
Thank you
Yeah,
very much, Mr. Josh, for your
yeah.
sharing and your experience with our participants.
Okay.
Uh, while we move to the second session with Mr. Hazri, maybe if there are some questions, you may text in the chat box, and then we will try to assist you. Right? Without further delay, I invite Mr. Hazri on the operations of the DSC.
Hey, hello.
Yep, I can hear you, Mr. Hazri. Yes.
Can you
Please
hear
proceed.
me, Mr. Sharon?
Yeah, very clear. Please proceed.
You see the slide or not?
Yeah. The slide appear. Okay.
Is it full screen, right?
Yeah, full screen. Yes.
Okay, thank you.
Yeah, thank you.
Okay, thank you, TS Mr. Shairul, for moderating this session today, and also thank you to our special guest, guest speaker, Mr. Josh, for the valuable sharing. Okay, Assalamualaikum and good afternoon to everyone. Thank you for your commitment given for attending this webinar. For continuation session, I will share on how to conduct the sample preparation, equipment demonstration, and data processing also, as well as result. Okay, before we proceed further, I would like to introduce myself. My name is Muhammad Azri. I have been in TP for 18 years as a lead technologist. Currently, I attach to Centralized Analytical Laboratory unit under Physical Cluster. Beside Mr. Shairul, I'm one of the individuals responsible for the DAC equipment. Okay, for your information, at CAL we have two types of DAC unit. The first is Q2000 DAC and the TA instrument as shown in this slide. And the second unit is the high pressure micro DAC Evo 7. Okay, the different these two units are the temperature range and also the scanning rate. So for Q2000, the temperature range can go up to negative, starting from -80 up to 400. However, for high pressure micro DAC, we start from -40 up to 100 degrees C. But another difference for micro DAC, we can set the scanning or heating and cooling rate starting from 0.001 up to 1 degree C. So this is a difference between standard DAC and also micro DAC. Okay, as explained by Mrs. Joss, the differential scanning calorimetry determine the temperature and heat flow associated with the material transition as a function of time and temperature. It provides the data for endothermic and also the exothermic processes of material during physical transition. Okay, here I would like to share the specification of the DAC to everyone. If you can see, this is our practice in our lab. The sample size is starting from 0.5 to 5 milligram. This is nominal. Temperature range that we can set is -80 to 400. Then for the scanning rate, we can set 1 up to 20 degrees C per minute. Okay, here based on this specification, the customer can decide the desired parameter for the sample. Okay, for type of sample, we have multi-type of sample that we had tested in our lab. First is a liquid sample like oil, wax, polymer solution, solvent material, and etc. Other than that, if we have a waxy crude oil sample, we need to heating up and shake it a bit, make it homogeneous. At the same time, we want to, for this crude oil sample, we want to study about the WAT, wax appearance temperature, and also wax disappearance temperature, WDT. Okay, the second type of sample is a solid sample, like a solid polymer, membrane, thin film, and fiber. We also have a powder sample, like a nanoparticle and cellulose. Bear in mind, to get a better result, ensure the liquid sample is homogeneous if it is mixed with various components. So the second is the temperature setting must not exceed the decomposition temperature unless if you want to study about the oxidation or evaporation. So we advise to the client to determine the decomposition temperature by using the TGA. Okay, we go to the sample preparation slide. First step is selecting the pen type and material. In our lab, we use aluminum pen material. So we have two different type of lead for liquid sample and also for solid sample. Mr. Josh already explained about this. So we have two type. For solid sample, we use a T0 hermetic lead, and for liquid sample, we use T0 hermetic lead, and for solid sample, we use T0 lead. Okay, for the second step, sample preparation, we will place the sample in the T0 pen. So T0 pen. So I would like to show you the video on how to do the sample preparation for liquid and also this for solid sample. The left video is a preparation of a liquid sample. And then you can see that we use the pipette, and then we drop the sample, the liquid sample, in the T0 pen. After that, we will record the weight. Okay, the right video show the sample for solid preparation for solid sample. For solid sample, we will cut it into a small pieces, and then we place the sample in the T0 pen and record the weight also. Okay, for the next step is encapsulating the sample in the pen using T0 press. Okay, this is a tool that Mr. George explained to you. And then after we measure the weight, we cover the sample with T0 lead or T0 hermetic lead and place it in the T0 press. The video show, okay, this one, the video show the encapsulating process. Okay, next, for sample analysis, once the sample pen has been prepared and the sample information has been recorded, you are ready to load the sample pen into the DSC cell. Okay, you can see the video. So the sample pen is ready, and then carefully place the reference pen on the rear left platform, as shown in the video, and the sample pen on the front right raised platform. And then we centering the pen will give more accurate result. After that, we close the lid of the DSC. Okay, In this video, we will show you the process to key in a sample information and create the experiment procedure using TA Instrument Explorer software. If you okay, so you can see how we key in all the information. We click to the summary, and then we select, we key in the sample name, pen type, sample size in milligram, pen mass, next, we click the procedure, select the test, and then we can set the parameter, the heating rate, upper temperature, cooling rate, and also lower temperature. We can create the multiple cycle for this test. At the same time, if you want to determine or you want to see the for the isothermal process, also you can set it based on your study. Okay, next we go to the result overview. I think this one, Mr. Joss already explained detail on the thermogram about the process of this thing. Before we go to data processing, the left thermogram, if you can see the left thermogram curve show the endothermic, where the heat absorption and exothermic heat evolution process of material. Okay. There are two types of phenomenon as shown on the thermogram, which endothermic for melting, dehydration, glass transition, denaturation, pyrolysis. For exothermic, peak for crystallization, oxidation, combustion, and decomposition. If you see the right thermogram, show the result from Q2000 DSC, where an exothermic or crystallization and endothermic for melting peak are observed during cooling and heating. Okay, the graph show for, you can also set the graph heat flow versus time. Okay, in this video, show you on how we do the data processing using TA Universal Analysis software. We open the export the data into TA Universal Analysis software for the result to be interpreted. Output from the analysis are either glass transition, crystallization, melting point, enthalpy, and also heat capacity. Our common practice, we will provide you we will share the result based on the raw data in the Excel format, and also the graph. So I believe this is a short presentation from my side. I believe this is the platform for us to get some knowledge. And then thank you so much to everyone for your commitment, attention throughout this session. Hopefully the shared information will feed you some valuable knowledge and experience. So I handing over this session to the moderator back, and thank you.
All right, thank you so much, Mas Aziz, for sharing the actual practice actually in the lab. But we noticed that the setting and parameters actually comes from the researcher or the customer itself. Sometimes they want only one cycle, which means only one cycle of testing. Sometimes the researcher requested for 2 cycle and sometimes three cycle, and there are cases for the 4 cycle testing. I can see in the meeting chat there are questions from Mr. Siwa. He has the polymer sample. He cooled down the polymer sample to negative 70 degrees C and then melted to 200 degrees C. And then next step, he cooled it to negative 50 degrees C and then melting it back to 200 degrees C at the heating rate 10 degrees C per minute. The result comes the enthalpy too low, and Mr. Siwa only used only 2 milligram. Mr. Josh, any opinion on this case?
First of all, I want to check, do you have any idea on your sample morphology and what type of sample is this? Is it thermoplastic materials or is it a well crystalline materials?
It's a polyvinylidene, which is actually has amorphous and also the crystalline as well.
Okay, so I
Yeah.
believe the small melting peak phase, it can be due to that you have a low crystalline phase, first of all, low crystal
Mm-hmm.
phase, and also your sample size is too low. Maybe you can increase like to 5 mg to check on this. And also I want to check your crystallization peak. Is it very small as well?
It's too small. It's about when I calculated the what do you call the enthalpy and also the crystallization, it actually
Mm-hmm.
cost me about 3 joule per gram, something like that. So it should be
That
about
is
330, something like that, actually.
very small, and you have to understand that only crystal phase will contribute to the peak, and the rest will be on the TG. Do you have a very significant TG in your results?
The TG was so significant
Yeah.
compared to, yeah.
Then that's the case for maybe you can increase the sample size a little bit to check maybe up to. Is your sample very bulky or is possible to increase the sample size?
I can increase the sample size, but the thing is that actually it's a polymer film. So the polymer film is quite thin, and when you put it in a pan,
Okay.
so yeah, I need to have a few stack it on top of each.
Yeah, it's
Will
okay.
that be
You can.
possible? Yeah.
Yes, it is possible. It's possible because you can use a crimping pan to push all the layers together.
Yeah. What will be your recommended, the weight of the sample? Will that be 5? Sorry for that. 5 milligrams or
I
10
think
milligrams? Yeah.
5 to 10 mg for
Okay.
your case. Yeah. I
Yeah.
think it can increase the peak, but the size I cannot guarantee yet because you have a very low crystal phase from the result that you described to me. Yeah.
Yeah,
Yeah.
the thing is that I've done SRD with that sample as well, but I found that through SRD, it actually has quite high crystals compared to the sample that I put in a DSC.
I see. Then maybe you can increase the sample size and check in.
Yeah, thank you
Yeah.
so much.
Okay.
Cheers.
Okay.
Thank you. Cheers.
Okay, thank you, Mr. Josh. And then we have second questions from Mr. Ahmad Kamal. Relating to slide number 40, to what extent in terms of temperature difference can those factors affecting the standard or benchmark of glass transition value of a specific polymer?
Okay. For these questions, to what extent in terms of temperature differences? Okay. First of all, you need to understand a TG is actually a range of. Okay, this is the first point. But usually we only represent them with either onset, set, or midpoint. Midpoint you have midpoint of inflection, midpoint of half height, midpoint of half weight. There can be slightly deviates, but factors that are affecting a standard or benchmark TG. Well, a TG, for your information, it is a benchmark for certain pure. I'm talking about pure polymer. When you started to add fillers, when you started to add plasticizers, when you introduce hydrogen bonding, when you introduce curing, it will eventually shift your TG to either higher temperatures or lower temperatures. Even you are using different heating rate in your DSC, it will also shift the TG. Okay, anything that you do that induce or molecule mobility, it will eventually modify the TG as well. Even you use a polymer blend, okay, it will also shift the TG. So benchmarking TG value, I do not use this as like, okay, the TG for this polymer is at these temperatures. Okay, it is not it's not like an FTIR method that you have a specific wave numbers that you can typically like a library to help you to identify these polymers is with this TG. TG cannot be used as an identification method as well as DSC. DSC is actually a quantification method. It's not qualitative method. Yeah. Hope this answered your questions.
Okay. The other one, Mr. Josh. The Mr. Abu Bakar. He's a postgraduate working on the development of polymer nano composites for flow assurance of waxy crude oil. His research focuses on mitigating wax deposition in pipelines. Based on your experience, what is the best polymer for this application?
Sorry, I'm not the expert in the wax research, so I cannot give you an exact answer on polymer for this application. So, yeah.
All right. Any other questions from our participants? Or even after this they have questions, maybe you can email, then I try to contact Mr. Josh or direct for the questions. So any more from the floor for the Q&A session? If there's no more questions, I would like to thank you very much for your time, for participating in this webinar. So we are happy to have Mr. Josh. He's our reference actually for this technical and also application. So before we left, I would like to request you to fill in customer feedback form for this session, and I do take note on the feedback from the registration form on the area and field that most requests and your area actually. Wait. Okay. Okay. This is the QR code for the feedback for this webinar, and then we will take note on the feedback earlier on the area as I said in the beginning. So with that, thank you very much. Any problems or any services required for Carl, you may email us, contact us, and we will try to assist you from time to time. Right, with that, thank you very much, everybody. Assalamualaikum.